Okay, I'm sure it's recording. All right, so we're going to start off by talking about graphs of polynomial functions. I'm going to again jump around these notes. So these notes are for the entire unit. Likewise, the homework. So everything should be all set. And I'll try to get this up Schoology later today so that everything's all kind of in there and populated. If not today, by tomorrow, I'll have that done. But yeah, let's talk about polynomial functions. And again, I'm going to skip around a little bit because some of these notes, you need a pencil or your iPad? Okay, got it. Yeah, because like later in the part one of the notes, there's another thing called power functions, but I want to save that for Thursday. But there's some stuff in part two I do want to talk about, like polynomial division, because your homework is going to involve a lot of it's called recall, just old stuff. Um, yeah, so like quadratic functions, there's stuff on that. You know, vertex form, word problems. So I might help you guys. The homework is kind of lengthy, so I might help you guys a little bit. Complex numbers should all be review from last year, but maybe a little rusty. Um, so I am going to skip around a little bit so you guys can feel empowered to do the homework. And hopefully you guys have a chance to get homework done in class today. All right, so let's start with page one. Okay, what is a polynomial function and behavior, power functions, whatever. So let's start with what is a polynomial function. So a polynomial function is just a collection of terms that are set up in such a way where you have x raised to some power, and the power you're raised to is going to be a non-negative integer, just so you know. So you can't have, like, for example, n here is going to be non-negative. So it could be 0. That's fine. But it can't be a negative number. Like, you can't have, like, y equals 2x to the negative 3 power. If you had that, what kind of function would we call that, by the way? If you had 2x to the negative 3 power? It'd be rational. It'd be 2 over x cubed, right? Well, we will talk about that in this unit, but not today. Actually, I do. I lied. We'll talk about that briefly today, but we won't go into great detail about rational functions till probably next week. But that's not a polynomial, just so you know. That's not. So you have to have non-negative exponents. The coefficients could be whatever. That doesn't matter. A sub n minus 1, whatever. The domains will be all real numbers. There's no restrictions. The range may not be. Depends on the end behavior, which is kind of a nice lead into the next thing we'll talk about. They are smooth. There's no sharp turns or corners. It's continuous, no breaks in the graph. So very basic stuff. That's the basics of polynomials. So now let's investigate the graphs in example 1 and see whether they represent a polynomial function. And so we'll give our reasons as well. So only one of these is a yes. The rest are no. Which one's a yes? C. Totally C, right? 100%. That's a yes. No, no, and no. Sharp corner. Why does that matter? We will actually talk about that when we get to the calculus unit, not until our last unit, unit 5, not until like after spring break, which is a long time from now. But we'll get there. I'll explain why sharp corners are not okay. It has something to do with derivatives, but we're not ready to have that conversation yet. For part B, it's not continuous. And likewise here, there's a vertical asymptote, also not continuous. Continuity means, can you draw the curve without lifting your pen or pencil off the paper? If you can draw the curve all the way through without lifting your pen or pencil off the paper, then it's continuous. Otherwise, it's not. To be more specific, oh my God, I'm so sorry. Geez, that's spam. My apologies. Hold on, sorry about that. I usually have my ringer off. That's so weird. My apologies. Okay, it's off. Okay. Yeah, I should have listened to Lamont, right? Really quickly, this is called a jump discontinuity. Do you guys see why that would be called a jump? Because the graph kind of jumps, right? So that's called jump discontinuity. We'll, again, investigate that when we get to calculus. This right here is called an infinite discontinuity. Why do you think we call it an infinite discontinuity? Because what? Yeah, y goes towards infinity, either to the left or to the right. The positive negative. So infinite nature to it. Of course, that's a vertical asymptote too. Um, or we could say it's a vertical asymptote. So anyway, let's keep on moving. Okay, and behavior. This is a big one. And we're going to be using this notation quite a bit. Limit notation. I don't remember, did we use this notation last semester? LAM? No, okay. So this is new then. Okay. Um, yeah, I should know that, right? I just forgot what we did last semester, right? So let me explain what this means. Let me break this down. LIM means limit. Here, this means X is approaching infinity. F of X is Y. And the question mark is a value. Let me replace that. Numerical value Y approaches. So that's how you dissect this. It's a kind of shorthand notation. You guys have seen it already. Like you could say as X does this, what does Y do? Like that's where you guys would write it. As X approaches, like for example, I'll do off the margins here. As X approaches infinity, you'd say Y approaches infinity, right? You guys have seen that at least, right? The way you write it as limit notation, you write like this. Limit X approaches infinity, F of X. Those are equivalent statements, just so you know. These are both 100% the same thing. So we just have to get used to writing in this way because when we start doing derivatives later in the year, we have to use this notation to help us with that. So that's what it means, just so you know. LAM is short for limits. X arrow infinity means X is approaching infinity. F of X is Y. What you get on the other side of the equation, the other side of the equal sign, is the numerical value Y approaches. So in this case, as X approaches infinity, Y approaches infinity, or whatever. Then you write limit X approaches infinity, F of X equals infinity. So does that make sense? We're good there? All right. And why we call it end behavior? We call it end behavior because you're looking at the ends of the graph. So clearly this is going to be the left end, and that'll be the right end. So generally speaking, this means we're looking at, actually, I just said it right now. The left end. And hold on a sec here. And give me one sec. I do need to print the filled out notes. Give me one sec. Sorry about that. Hold on a sec here. Just gonna freeze the screen because it's got to take care of some really. Hold on a sec. Stop. Hold on, my mouse is not working. One sec. Sorry about that. Pause. Yeah, Eddie, let me print those notes for you. Hold on a sec. Sorry about that. Eddie, do you still need to fill out notes right now? Are you okay? Okay, when we're doing some practice problems, I'll print them right now. Hold on. Just realize that. Yeah, you stay good.
Think about number act. What would you say as y equals to 0 when y negative?
The limit does not exist. You have to do a one-side limit. We'll talk about that when time comes. We'll have that discussion when we talk about rational functions. Yeah. Which we should do in this unit. All right. Sorry, it's just taking a little while to print some stuff here. Okay. Let's get back. My apologies. Okay. Hold on. All right, we're back. Okay. Yeah, so again, we're looking at the left and right ends of the graph. All right, so let's look at these here. And I don't think we necessarily need to use a graphing calculator. I think we can kind of tell what's going to happen. Like, okay, x cubed. I know how x cubed is going to look. It's going to look generally like this. Oh, you're right. Thank you. Yeah, so y equals x cubed looks like that. Look at the left end of the graph. Where's the left end pointing? So you can put negative infinity. How's the right end pointing? So that's all you're looking at is left and right ends. That's why it's called end behavior. So you have to set up this way to show that you're describing the end behavior. X approaches negative infinity does this. X approaches positive infinity does this. So when you have this here, x cubed minus 2x squared minus x, obviously it's a different graph, but it's still gonna have the same end behavior. Okay, still gonna have the same end behavior. So hold on a sec here. Let me freeze again really fast. Go to Desmos. Yeah, if we go to Desmos, we do y equals x cubed minus what was it, Sean? Yes, minus 2x squared minus x. Sorry, a little rusty here. Minus 2x squared minus x. Okay. Yeah, I mean, obviously there's x-intercepts, y-intercepts, all these things, these hills and valleys, but still the end behavior is still the same. That doesn't change, right? So that's still the same. Now, if I put a negative out in front, like if I do negative 1/2 x to the fifth, if I were to graph that, the graph's gonna look like this. So that's what happens. You have a negative because there's flips, right? It kind of looks like x cubed in some ways. So you can expect the same thing, even if you have all this other junk here. How come the other junk doesn't matter? Like the negative 3x cubed plus 2 or negative 2x squared minus x for part A. How come these two terms don't matter for the end behavior? Yeah, the exponent's smaller, exactly. When you look at end behavior, you have to look at the term that dominates. What's going to dominate? The higher exponents. If I plug in like a large number for x, like if I plug in 10 for x, what's that going to become? 1,000. That's going to be negative 200 and negative 10. Clearly 1,000 much larger than these two here, right? That happened. So we expect it to dictate the x2 to dictate the end behavior. Well, if x2 looks like this, yeah, there you go. Likewise here, right? Negative 1/2 x to the fifth power. So if x is really big again, like I put like 10, that's going to be I think 100,000. So that's much bigger than these other two numbers, right? And that's a negative next to it. So if you plug in 10 or 100 or 1,000, whatever for x, y is going to be going towards negative 50. That's what's happened there. Okay, let's keep moving. 2x4. How do you think that's going to look generally? Oh, I'm sorry, John. Let me take care of that. There we go. There we go. Right. Um, yeah, how's that going to look? It's going to be kind of like a parabola. It's not really a parabola, but it kind of looks like it. So you expect this. And think about it. If you raise one to the 4 power, will it ever be negative? Never, right? So who cares if you have negative 3x cubed plus x minus 5? Whoop-de-doo. It's all about the top, the highest term, right? The term with the highest exponent. That's what you want. Then here, you're going to expect this. So what do we notice? We have to focus on the leading coefficient and the highest exponent. What do we call the highest exponent? Is a term that we call it. What do you guys call it? Degree of the function. That's all you look at. For the leading coefficient, what do we care about? Whether it's positive or negative. The highest exponent, we care for whether it's even or odd. That's what we care about. Here we're good. Okay, let's look at the next one. So again, a sub n, if that's the leading coefficient, we're looking at whether it's positive or negative. And here we're looking at whether it's even or odd. So this is just kind of repeating what we just wrote. So if n is even, your graph could look like this. Kind of like the arrows go in the same direction, if that makes sense. Odd, the arrows are odds with each other, going opposite direction, if that makes sense. Again, this is when a sub n is positive. Here's when a sub n is negative. Here when a sub n is positive, a sub n is negative. So ultimately, you could be pointing up if you're even degree, positive leading coefficient, pointing down, even degree, negative leading coefficient. Odd degree, opposite direction for arrows, but ultimately it's going to be going up towards the right. If it's positive, down towards the left. If it's negative. So if it makes sense how to do those problems, that's pretty clear. Okay. Let me show you the homework. I don't think you're gonna. Actually, I do want to jump to one other problem before I go over the homework. We're gonna skip part B for now. We'll do that Thursday because the homework doesn't quite correlate to that. But let's jump to page 6, example 2. Let's take a look at this one here. Ultimately, you guys can get very good at these graphs. You won't be able to quite tell how high or low some of the peaks or valleys are. You will when you get to calculus. And maybe in the spring, if we get a chance, we can talk about that calculus. If not, you'll do that in the second next year. What do you think the degree is for the function? If you were to expand it, don't expand it, by the way. Please don't do that. That'll take too long. Don't foil it. But if you were to imagine, like, what would be the highest exponent? What do you think it's going to be? 5. Right, because you have an x minus 2 squared and x plus 3 cubed. So degree is 5. Okay. What do you think the x-intercepts are for this graph? Yep, 2 and -3. Now, if I had x on the outside, if I had negative 5x times all that junk, 0 would be as well. Okay, multiplicity. Do you guys know what multiplicity means? Have you guys talked about that? How often? Yeah. So x equals 2 twice. Oh, there you go. Look, Sebastian. Nice. X equals 3, -3 3 times. Yeah, I'm skipping around. Sorry. Okay. We'll talk about what that means in the graph in just a moment. Part D, determine the graph's and behavior using limit notation. Okay, let me do part D over here. you're gonna write like this. You really want to get a habit, and you can't get lazy about it. You really have to kind of embrace this way of writing it. Okay. What's my leading coefficient, by the way? What will be the leading coefficient, guys? Perfect. So, and if it's an odd degree, I expect the arrows to look like this, right? They gotta go opposite direction, but it's negative leading coefficient. It's gonna look like that. So it's gonna be positive infinity and negative infinity. Okay, and then I'll do a few tick marks. Y-intercept, we should probably figure it out. It's gonna be kind of a crazy number. If you plug in 0, you should get. I'm gonna calculate that. Hold on a sec here. Just calculating it. So you're gonna have plug in 0, you should get negative 20 times 27. Should be negative 540. That's like really low. Yeah, that's like crazy low. By the way, when you have an x-intercept that has an even multiplicity, you know what that does graphically? You said Sebastian earlier.
Yeah, bounce stops.
It bounces, right? Okay. And if it's an odd, it crosses. Do you guys know why? I'll explain in a moment. If you're not sure why. So you're gonna have an x-intercept right here, right here. Graph's gonna, geez, hold on. Okay, that's how the graph looks. Now, why do you see a bounce there? We see a bounce because if I do a sign chart, I don't remember if I did sign charts with you guys. Did I do sign charts with you guys last semester? So that's where you kind of do like a number line like this. Yeah. Again, I don't know why I forgot what I did with you guys last semester. I think I'm just so moving on to 2025. I should know, but anyhow, if you were to plug in a number larger than 2, like say 3, for example, overall y would be negative. Correct? Like if I plug in like 3 for x, 3 minus 2 squares is positive, 3 plus 3 cubes is positive, but in times -5 makes it negative overall. What if I plug in something less than 2, but greater than -3? Let's say I plug in 1, for example. Well, you're still squaring x minus 2, right? So who cares if the inside's negative? You're squaring it. 1 plus 3 cubed, that's positive still. But you still have the -5. So there's no sign change because where did that 2 come from? It came from an even exponent, right? Can even exponents ever produce changes in sign? Never. So all exponents being positive. Of course, if they're negative outside of it, fine. But that's not going to cause a sign change. Even exponent. Whenever you have even exponents next to a factor, you never ever see a sign change. Never. But odd exponents you do. Hence, and because we're looking at the sign of y, if y is below the if the graph's below the x-axis to the right of 2, it's going to be definitely below to the left of 2 until we get to -3. That's why you see a bounce, because of the even exponent. That's the reason why. So we'll do a lot of sign charts. We'll get the rational functions. That's kind of a big deal. Lastly, for part F, was the maximum number of local extrema. Extrema is the plural for extreme. So we have like a low point and a high point. So you have 2. You could have up to 4. Whatever the degree is, and we'll talk about this later in this unit. Whatever the degree is, the maximum number of extrema is usually going to be 1 less than a degree. But in this case, the way it's set up, you only had 2 extrema. And I'll talk about local, like what that means, like why we call it local. We'll have we'll kind of explore that later on. For now, I just care about you graphing it, because on the homework, I think there's one question where you have to do something like that. Yeah, number 11. You have to do that. Oh, by the way, going back to the graph again. I think it's pretty obvious that the y value here is 0. I don't know if that's true the lowest point though. I don't know if it's at negative 540. You're not going to know that until you start learning calculus. So I don't know truly what the lowest point is. The best way for you guys to tell right now is use Desmos or graphing calculator. And again, we'll explore that when we do more polynomial graphs later in this unit. But for now, just want to make sure you can understand the end behavior, understand the x-intercepts, the bouncing, crossing, all that stuff. Okay, cool. That's one thing I want to talk about. The other thing I want to talk about was polynomial division. Oh yeah, let's look at this one here. Yeah, okay. Oh goodness, those are kind of crazy. Let me see what's in the homework. Yeah, there's some stuff like that in the homework. Okay. All right. Now I have to ask in Mr. Band's class, when you guys did you guys do polynomial division? Yeah, I know I didn't regular algebra 2. I don't know if you in algebra 2 trig honors. Do you guys use like long or synthetic or
Yeah.
do you guys do some of the box?
It's like synthetic.
Did you guys do something like this though? They call it polydoku. Okay. I'm gonna give you two techniques. You can choose what you want. Personally, I like the box method. I think it's pretty cool. Long division, if you want to do it, it's fine. I'm not going to hold it against you. So let's do long division first. Okay, long division. And we go to what time today? 9:40. Okay, we got some time. We're good. All right. Okay. You guys remember how to do this? No? Okay. What do you multiply? So here's what you do. Actually, let's back up a little bit here. Let's back up just a tad. What if I had like 546? I don't know why I came with this number. Divided by 7. Okay. Or well, actually, let's divide by 5, let's say. Actually, I should have done 456. You guys know what that means from Squid Game? Player 456? No, no one watches. Okay. See, yeah, you know. By the way, it's got some really cool math in it. We try to figure out how much money's left after certain players get eliminated.
There's like a million after.
Well,
100 million after
40 billion.
Well, that, but then also, but then one of the games is like how many players could be remaining after. I don't want to spoil it. I'll stop. No. Well, no, I know it doesn't. I get that, but to divide it and then convert it to American dollars. That's what I meant. The conversion set. That's what I meant. Yeah.
Have you watched these games?
No, I get this. 45.6 billion won. I know. I get that.
The English sounds terrible.
Dude, no, I tried to watch it in English and the voices are just so bad.
Okay.
I just
Yeah, I should be talking about a TV show that's got some brutal, violent scenes in it. But anyway, guys, you guys remember how this works? Okay. Sorry, I digress. My fault. Okay. So how many times does 5 go into 5? Once. So you do that. Then you subtract. Then it goes in and then you bring the 6 down. How many times is 5 going 46?
9.
Wait, I messed up somehow. Hold on.
I think
No, there should be a 0, I think. Yeah, there should be a 0. My bad. My apologies. See, that's why I don't like it. Then 46, and that goes in 9 times. You do 45, you subtract. So what you do is you have to look at the outside, see how many times it goes onto the inside. So if you look over here, what do you multiply x squared to get to x cubed? X, right? Yeah. They have x cubed. But it's kind of nasty because you have to subtract. Okay. So what you do is multiply x squared by x to get to, because you're trying to ask them, what do you multiply to this to get to this? Just like, what do I multiply to 5 to get to 5 here? So if we're present to this, right? What do you multiply 5 to get to 5? 1, right? The same thing here. What do you multiply x squared to get to x cubed? X, exactly. But then you have to multiply x squared plus 1 by x. If you do that, what's x squared plus 1 times x? X cubed plus x. Then you got to subtract, just like that over here. And if 5 times 1 is 5.
Oh, but there's no X squared for you.
Exactly, right, correct. Correct, right, there's no, so when you subtract, you get this. Okay, what do you multiply x squared to get to, negative 3? And it actually comes out nice and clean. You get no remainder. So there you go. So all this just equals x minus 3. So that's how you can do long division. It can get nastier if you get remainders or other weird polynomials, but that can happen. So that becomes x minus 3. Now I'm going to leave up the long division up here so you guys can simmer on that if you guys want. But let me show you the other way that it's supposed to be taught in CPM, which now you guys saw Mr. Band did not do with you guys, which is totally fine. But you may like it. I think it's cool, but I'll leave it up to you guys. Here's what you do. You make a box and you ask yourself, what's the degree of the top polynomial? What's my degree of the numerator? So you're going to create 3 columns or two partitions. You're going to put the leading term in the top left corner, and you can put the last term in the lower right corner. And you can put x squared and 1 off to the left. That's how you set it up. Okay, so that's the setup. You put the leading term right here. You put the constant right here. You put your divisor or your denominator off to the left. Now, this is what you do. You ask yourself the following question. What do you multiply to x squared to get to x cubed?
X.
Okay. And what's 1 times x, guys?
X.
X, okay. So you put an x here. Okay, cool. Now, if we think about it, oh crap, I messed up. Sorry, I messed up, guys. I'm supposed to do another another row. My apologies. I just realized it. I realized my error in my ways. My apologies. I was supposed to do that. Yeah, I have to do this. X squared. I have to put a placeholder for x. My bad. I forgot to do that. Okay. Redo. My apologies. I got this. You gotta put a placeholder for the x. I should have actually done that over here as well. I didn't, but it's okay. But you gotta put a placeholder. Now let's do it again. Yes, that's gonna be that'll be x. So I'm gonna write this as 0x squared and positive x. Okay. Now, if you think about it, I have negative 3x squared, right? I have negative 3x squared. So I have to put a negative 3x squared right here. What you want, I know this is the part that's a little confusing. You need these terms to add up to that term over here. So if you have a 0x squared, what has to be added to 0x squared to get to negative 3x squared? Negative 3x squared. So if there's a negative 3x squared, then we're only multiplying for this to get to negative 3x squared. Negative 3, exactly. I'm going to do this one more time so you guys can see it done one more time. But what you have to do is you have to make sure all the terms inside add up to what you're multiplying into, or sorry, dividing into. Then this becomes negative 0x, or just 0x, I guess. And that becomes negative 3. At that point, now we also need, the other thing we need is this, is that we need this to be positive x. have a positive x, I have a 0x. So this has got to be a 0 again. So there's nothing more to multiply at this point. And that's why you get x minus 3. I probably didn't do the best job of explaining it. Let me show it one more time. But
You get the bottom right. One time.
yeah, I think I messed up somehow. I just realized I think I made a mistake somewhere.
But.
You need a fourth column.
No, because they should everything should have to -3 in the middle. Actually, that would wind up becoming 0. Yeah, it actually should be a 0. So you should get that. Yeah, that's what it should be. You did it correctly. Well, let's try another one, guys. I promise I'll do it better. I promise I'll do it better.
How do we know where the last one goes at the start?
You should go in the lower right corner, but in this case, that didn't happen because of the weirdness of this situation. Let me show you another one. Yeah, I should have done 2 columns. You're right. I should have done 2 columns. Well, that was a unique case. Guys, let me try one more time. Guys, I got this. I got this. Here, we got it. Here we go. Let's see one more time. Here we go. All right. Yeah, 5 columns. Sorry. Here we go. No,
Why is that 0? What isn't that supposed to be?
it's a constant. Okay. Okay. Hold on. Why is it showing that? Hold on. My screen's acting really stupid right now.
You have a negative to it. It was right here, right? We gotta cancel.
Okay.
What's that?
Hold on. I just messed up, guys. Give me a sec. Let's try again. But how do I get rid of, why is it? Oh, goodness. All right. Sorry, guys. Struggling here again. Okay, I got this. Here we go. All right. So we're going to do 5 columns. 1, 2, 3. So 4 partitions. 2x and 1. 4x5. There's 0 here. Because it's plus 0. And remember, there's 0x4. Okay. So now, what do you multiply to 2x to get the 4x5? 2x4. So that becomes 2x4. Now, do we have an x4 in the numerator? So you're going to make that negative 2x4 here. You see why I made negative 2x4? So that becomes 0, right? So now this has to be negative x cubed. Okay. So what's 1 times negative x cubed? Negative x cubed. Now I need negative x cubed in my numerator, so that's going to be 0x cubed. So it's 0x squared. So it becomes 1. Okay, let's back up.
The negative 3x.
Okay, so I get negative x cubed. You guys see this, right? Okay, but we'll have your negative x cubed. So I don't want to add to this.
You just add to them. You don't want to.
You add, exactly. Here you're adding along the diagonals. So it becomes 0x squared. So that becomes 0x squared. So now this becomes 2x squared. So it becomes x. And that's x. And then lastly, that becomes negative 2x. So it's negative 1. But because you got negative 1 over here, that's going to be your remainder. That's going to be your remainder.
Should have paid attention. I literally was the
So the answer would be this. Exactly. Because you're supposed to have a 0 there. but you didn't get a 0.
So we don't.
You could, but because it becomes -1, that's the remainder. So the final answer becomes this. So that's how the division's done. And we'll spend more time at this later in this unit. But you're going to have some problems where you have to do that on the homework. So I want to make sure you guys saw that. Now, there's still yet another technique. You guys do synthetic division with Mr. Ban? Okay, let me do, well, actually, synthetic's going to be tougher for this one. So I'm going to not do it this one. We'll leave it at that for now. Now, how do you know we did this right, guys? Here's how you know. You could just graph the polynomial. So if we do y equals, or sorry, graph the function itself. So if we do y equals, hold on, x 4x5. Keep going.
Plus 2x squared.
Sorry, 4x cubed minus x.
Plus 5 minus x cubed.
Mm-hmm.
Plus 2x squared.
2x minus x divided by 2x plus 1. Okay, so it looks like that. Now, if I graph my answer, it should be the same thing. Because really all you're doing is a cosmetic change. Hold on. No, did I do something wrong?
Is that a plus? I guess.
Yeah, 2x plus 1. Oh, hold on. Maybe there should be a plus. Oh, there we go. Yeah, that should be a positive 1. Yeah, so let me explain that. So the remainders make it a little funny too. So this is supposed to be a 0. Oh goodness. I just messed up my box again. Okay, so yeah, so it's supposed to be a 0 here. So we had to put a 1 here to balance that out. That's why it's a positive 1. You had to put a 1 to balance it out. To get a 0 in the middle. That's why. Yeah. Don't worry. We'll clear this up. I didn't do the best job explaining it. I'm a little rusty, guys. I apologize. But it should have been a positive 1. Because when I graph the quotient should have been the same as the original expression.
Put another 1 doesn't mean no remainder.
Well, the thing is, you're supposed to have 0 as your constant, right? Yeah, because this is supposed to be a 0 here. So it's not, right? Because you have 1 times negative, which is -1. So you have to put a positive 1 here to balance it out.
So if we add a 1, we want more remainder.
Well, no, that guarantees a constant of 0. So the 1 becomes the remainder to guarantee that. You want a 1 here to balance out that -1. You see how I got -1 to 1 times -1? If I want, see, like, look at all these other terms. I want these to add up. Because I want the constant to go away. Yes, you can. Okay, what if this were a 2 here? What if this were a 2? Then I have to put a 3 here, right? Because then -1 plus 3 gets me 2. Then it would have been this as my remainder. So that's what would happen if you had that.
No, you gave us that.
I probably should give you guys an easier one to do first. I gave you guys a tough one. We'll come back to it. Don't worry about it. One last thing I want to talk about, and then we're done, guys. Then you guys go ahead and start homework. Let's look at graphs of rational functions. I'm going to jump to, and I think you guys know complex numbers, so I'm not worried about that. Here we go. Okay. And let me look at the homework that you guys have to do. Okay, here we go. All right. Let's go to page 21, example 1. So page 21, example 1. All right. I think you guys did do this last year. You're gonna want to do this first. Okay. Oh, page 21. Okay. Do you guys remember doing this in algebra 2 trig honors? These types of graphs? Find vertical, horizontal asymptotes. Yes. Okay. So, so you have to find a few things: x-intercepts, bless you, y-intercept, vertical asymptotes, horizontal asymptotes, and we're gonna do something called a sign chart. Okay. What are my x-intercepts? What do you guys think? What are they going to be? Yeah, because it's where it makes the top 0. Because remember, the top is 0. Y is going to be 0, right? Remember, we have an x-intercept. You want y to be 0. That's going to happen when the top is 0. Okay, where are my vertical asymptotes? Exactly. Correct. Do you guys know how to find the horizontal asymptotes?
This is at the top, there's right the top.
Yeah, so what you want to do is you want to look at the degrees of both top and bottom. So you have to think about end behavior, right? In some ways. That is what it is. It's all the end behavior, horizontal asymptote. If you look at both these degrees, these are identical degrees, right? So they both increase at the same rate. If I'm putting like 10, for example, I get 200 minus 2 and 100 minus 4. Overall, it's getting closer to 2. If I'm putting like 1,000, I get 2 million minus 2 and 1,000,000 minus 4. Overall, it gets closer and closer to 2. So what's going to happen is that when you compare the degrees both top and bottom, it's going to get closer and closer to 2. That's because it's a limit situation. You're looking at the limit as x approaches positive infinity of f of x, and also looking at the limit as x approaches negative infinity of f of x. Whenever the degrees are the same, you take the ratio of the leading coefficients. Now, what if it was just plain old x up top? What would it be? Y equals 0 because the bottom has a higher degree than the top. The bottom is increasing faster than the top would, so overall fraction is getting closer to 0. Now, we're not ready to have this discussion yet, but what happens if the top is a higher degree? If you have 2x cubed, there's no horizontal. Instead, you have to do something called a slant asymptote. I mean, you're going to have to do long division or synthetic division or the other division I showed you guys. We'll cross that bridge later. But for now, you have this. My y-intercept should be 1/2, I think. Yep. When I do my sign chart should come out like this.
Smarter than you. Well, yeah, that's true.
Okay, so positive, negative, positive, negative, positive. Okay. And why does that make sense? If I plug in 3, everything's positive, right? And because all the factors happen an odd number of times, you're going to see a sign change. I mean, you can test them if you want. You could plug in 1.5, you could plug in 0. But personally, when you do sign charts, which I'll talk more about later in a minute, I would test the rightmost interval first, see what happens to y, and if all the other factors are happening an odd number of times, you will see an alternation of signs. You don't have to waste time to test in 1.5 or 0 or negative 1.5 or negative 3. It will alternate nicely as long as if you have an even exponent, then sure, make sure there's no sign change. So I expect my graph to look something kind of like this. It does dip above the x-axis just for a tad. And there you go. That's how you do the graph of that. So we'll do more of this because these can get pretty complex later on. I think that's as far as I wanted to go for today. I think we're good for today. You guys should be able to do the homework. You can get a head start. The homework is just going to be pages 1 through 8, I think.
Recall problem?
The recall problems, yeah.
Oh, nice.
The homework is set up by there's 7 assignments in the packet. Let me freeze the screen here. So we're still copying.
Yeah.
So the homework, actually it's pages 1 through 7. So you're doing numbers 1 through 12. Yeah, so you're doing this.
1 through 12? No. No, that's crazy.
That's homework. Until I get a chance. Not due till Thursday.
Oh, okay, okay.
Yeah, because we don't meet again until Thursday. So
Wednesday.
How do you?
darn. Downstairs. Yeah.
How do you figure out like the top, like
Wednesday?
those options to take it last week?
So
No, that you like forgot those.
like 3 or 4 or whatever.
Oh, my God.
So I know it's positive. If I tell you why you have a large.
You send me my results from the last one again?
I'm multiplying a bunch of positive numbers.
Okay,
so what happens?
It's above the.
The average act as guardrails. For the graph.
And then, dude, how do you know?
It's
if
Just pick one every day. I think.
It's not going to do.
No, not every day, wait, every week, every week, every